so right now we're going to learn how to write net ionic equations. It's really important, if you haven't done this already, look back at the solubility rules video before you watch this. Our goal right now is simply this. We want to find two ions, then when we put them together, the rules tell us that they are insoluble. What rules am I talking about? Well, you best have this table out the whole time that we are talking. This table right here. So we're going to follow the rules in order, A, B, C, and D. But what we're going to do is we're going to apply them to double replacement reactions. So the best way to do this is to jump right in and use an example. So whenever we have a double replacement reaction like this, we're going to try and match them in a do-si-do manner. Now, if you remember how we talked about this, if we try and match them, we're going to try and put nitrate together with potassium, and we're going to try and put silver together with chloride. Now, all we have to do is try and find a rule that applies to either of the two things in a pair. Think of it this way. If one person asks another person out for a date, if that person says no, it doesn't matter if this person says yes. You don't have to have both people come up to each other and go, no, I wouldn't go out with you. Oh, I wouldn't go out with you, which I don't think would be a healthy thing to do anyway. All it would take is one ion, let's change the ion world, coming up to another ion, and one of the two of them saying, nah, I don't want to be with you. I am soluble. So the number one thing that we do is that we look for ions that are spectator ions, ions that do not form solids. If you look through the list, we're always going to follow the ABCD rules, and I'm always on the lookout for ions that always are soluble no matter what you put them with. So nitrate happens to be one of these. In fact, if you look at your solubility rules, nitrates are always soluble. Well, what is nitrate trying to hook up with? It's trying to hook up with potassium. So we know that nitrate, no matter what, it will not hook up with anything. So it doesn't matter, even if potassium wanted to hook up, in other words, even if potassium was insoluble in general, it's not going to be able to hook up. But as an added bonus, let's just say you forgot the nitrate rule. Potassium is part of group 1, so therefore it wouldn't want to hook up either. So it's kind of a double whammy. Both of them, when they come towards each other, are going to be like, no, I want to be soluble. That leaves us with silver and chloride trying to put them together. Now, if we take a look at the rules, there is a rule in the table for chlorides, and that's the group 7 rule with NAGSAG. Now, normally, chloride would be soluble always, unless you put it together with polar bears hug aggressively. So let's just write these things out. See, I have a Cl minus right here, and this is Ag plus. And by the way, just a gentle reminder when we're writing net ionic equations, they are ions in these ionic compounds. So when they get pulled apart, they become individual ions. So I'm trying to put these two things together, and because polar bears hug aggressively, this is part of it, these two things, when they hook up, they will be insoluble, which is what we live for, and this would end up being AgCl as a solid. What are the other two things? These two things up top here, we call those spectator ions, because when they bang into each other and they do a solubility check, they don't do anything. They just sit there. Let's try another one. Again, remember, what we're going to be doing is we're going to be putting we're kind of doing that FOIL method in math. We're going to put the aluminum and the nitrate together. Oops, that's what I really meant to do. And the calcium sulfate together. But as I said, I'm always on the lookout for spectator ions from the beginning, and nitrate is a big one. Nitrates never form with anything. So I would suggest this, before you even start writing out all the ions, but if that helps you, you can, I would look at nitrate and go, nitrate can't hook up with anything. Therefore, when it's trying to hook up with aluminum, it's not going to hook up. We call those two things spectator ions. That leaves us with calcium and sulfate trying to hook up. Now, I'm going to write these out because I kind of know in advance that these are going to hook up. But how do I know in advance that these are going to hook up? Well, I look through my solubility rules, and I see that sulfates are typically soluble. So normally, if I put something with sulfate, it wouldn't do anything. We'd have a no reaction. But calcium's part of Cal Bear Stir peanut butter, which means, again, that's look through the rules, that means that calcium wants to hook up with sulfate, and you will end up with CaSO4. Now, before I go any farther, let me remind you of something. If, let's say that this hadn't been calcium, let's say this had been lithium or any other element other than, or any other ion other than Cal Bear Stir peanut butter, we'd have no reaction whatsoever. And it's not uncommon to have nothing want to form. Much less common is having both things form, and that can happen. But just note here, this is a net ionic equation because I'm only putting the things that are involved in forming a solid together. I also want to bring something to your attention here because this is automatically balanced. I have one Ca, one SO4, one SO4. If I had two SO4s on this side, work with me here, it's not this example, I would have to put a coefficient in front of this to balance it off. Let's try lithium chromate and calcium nitrate. Again, these are ions, and just to give you an idea of what's happening in real life, what we have going on here is we have lithium, Li+, chromate, CrO4, 2-, calcium, Ca2+, and nitrate, NO3-. There are trillions of these, and they're just floating around. And every time they hit into each other, they do a solubility check. So when lithium hits into chromate, they do a solubility check. But if we notice up here, it says aqueous already. That means that we know that that's soluble. So every time lithium hits into chromate, it's gonna be like, nah. Same thing with calcium and nitrate. So the only two options we have for different combinations that might possibly hook up are the innies and the outies. So when lithium tries to hook up with nitrate, when these two try and hook up, they'll do a solubility check. Now, if you follow the rules, nitrate's a big one. Nitrates never want to hook up with anything. They're almost, and by almost, they are always soluble. Similarly, lithium is in group 1. They are always soluble. So all it takes is one of these two saying that we are soluble, and then those two will not hook up. But in this case, we are fortunate, and both of them say we do not want to hook up. That leaves us with calcium and chromate. Now, if you look at our rules, there are no rules, and I'm jumping ahead because I know the rules, but look right now on your own. Is there a hydrogen in there? Is there an OH-? And then look through the NAG/SAGs. Is chromium or calcium any part of NAG/SAG? Now, calcium we saw before, but that's when it was hooking up with a sulfate. There is no rule for calcium hooking up with chromate. So whenever that happens, we're going to go to the sweeper rule. And the sweeper rule says, if you don't know, if there's no rule that can be applied, you take a look at your negative ion and see what its charge is. Now, I'm going to write the ions down below here just so we can see them a little more clearly. This is calcium, this is chromate. Now, you may have noticed here that I could have written chromate directly below this and calcium after it. And that's perfectly okay to do. These two are going to try and hook up with each other. I put the positive ion always first when I'm doing my net ionic equations, because when we put them together, every compound always has a positive ion in front. The last thing we want to see is chromate calciumide. But if we look at these two here, isn't the charge on chromate, since no other rule applies, the charge on chromate's a 2-, which means it is insoluble, which means that these two will form, and they will form CaCrO4. And again, when I put CaCrO4 together, behind the scenes, I balanced off the 2+ and the 2-, and they came together. Let's try one more. Again, I'm always going to be on the lookout for things that can cancel or are spectator ions. So when I look at this, and again, I'm hoping that by this time you realize we're going innies and then we're going outies, and we're trying to hook these two things together. That's a pleasant sound. So I'm always on the lookout for something that I know based on the solubility rules, the A, B, C, D, will never hook up with anything. So one of the things that I know is that group 1 never wants to hook up with anything. Additionally, there is a rule for chloride. Remember, group 7s are always soluble unless you're putting them together with polar bears hug aggressively. So in both these cases, both with sodium and with chloride, they won't hook up. That leaves us with aluminum and hydroxide to put together. Is there a rule for either of those two? And the answer to that is yes. The second rule, or the B rule, is a rule for hydroxides. And it says one strong cal bear will not hook up. So what we have here is we have Al3+, and we are trying to hook it up with OH-. The rule says that if you have this B, anything in group 1, so look in group 1 and see if Al3+, and let's be honest, it's a 3+, so it's not going to be in group 1, or calcium, strontium, and barium, this won't work. But anything else here will, and Al3+ counts as anything else, which means that it will be insoluble, which is what we look for. So when we balance these two things out, we're going to end up with Al3+. OH in parentheses 3. Now, this is where it's really important. Up to this point, we've had things that have balanced perfectly. This is my net ionic equation. Al3 plus OH minus goes to AlOH in parentheses 3. Really important you have the parentheses there. Don't I have one OH here and 3 OHs there? So to write my completed net ionic equation, I have to put a 3 right here. Now, I could do many, many more examples of this, but I hope that giving you these 3 or 4, 3 actually, you have an idea of how to use the solubility rules to write net ionic equations. We will be practicing a ton of these. Hopefully this has been helpful for you. You have a blessed day.